So we're looking at linear transformations from a vector space V to W. And if W is the same as V, which is a linear transformation from V to itself, that's called a linear operator. So every vector V goes to some vector T of V inside of V. And what is called the image of T, or T of capital V, is all the vectors in V which come from some vector in V. Everything you can write is T of V. Or all W in V, which can be written in the form T of capital V for V and V. So just to give an example, suppose we have T from R2 to R2, and it's defined by T of XY is X0. So here's R2. Here is a vector XY, and it gets sent to the vector X0. So if this is V, this is T of V. So this is just projection of a vector onto the x-axis. So in this case, the image T of V, this is all vectors of the form T of XY, for XY in R2. This is the same as all vectors X0, or any X in R, which is just the x-axis. So in this case, T of V is just this line, this subspace. So T projects the vector onto the x-axis. That's what the image is. That's what T of V is in that case. And so T of V, think of this as T to the first power of V. Well, it's certainly contained in V, and we usually define T to the power 0 of any operator to be the identity. So T1 of V is certainly contained in T0 of V, because this is the subspace. And the problem on page 237, number 14, is to prove, this is A, if you take the I plus first power of T of V that's contained in T of I of V for all I. So, and how does one prove that? Well, so a vector W is in, so again, you have to understand, what does it mean when you take the power of something? So T squared of a vector means T of V. You apply T twice. T cubed is T applied to T squared of V. Or it's like you say, take V, take T of V, T of T of V, and then T of T of V. You just apply the operator 3 times. Like you have V goes to T of V, and then you apply T to this, you get T of T of V. And then you apply T again, you get T of T of T of V. T of T of V, that's just T, that's just the definition, T squared of V, and this is the definition of T cubed of V. So if W is in the I plus first power of V, that means there exists a vector V in the vector space such that W is T to the I plus first of V. That is, you take V and you apply T times. This is T applied to T to the I of V. What does it mean to apply an operator I plus 1 times? You apply it I times, and then you apply it 1 more time. But T to the I of V is just some vector in this subspace. So this is contained in let me say it like this. So, so we have, first of all, T of V is contained in V. Because if this is V, sitting inside of it is T of V. What about T squared of V? So T squared of V let me make it easier. Remember, T to the I plus 1 of V, T to the I of V means you take a vector V, you take T of it, T of that again, T of that again, and so forth. You apply the operator or the function T I times to V. So T to the I plus 1 of V, it's like you could say you take T of V and then you apply T to that I times. So altogether it's I plus 1 operations of T on the vector. But T of V is some vector in V, so this is contained in T to the I of V. If you take the I plus first power of T applied to V, that's the same as the ith power of T applied to T of V. T of V is just some vector in V, so this is the ith power of T applied to some vector in V. And if you think about that for a while, that is the proof. That's the proof. T to the I plus 1 of V is contained in T to the I of V. And if you have, for example, T cubed of V, we know is contained in T squared of V. But if T cubed of V is actually all of T squared of V, then T to the fourth of V, that means T of T cubed of V. A T cubed of V is T squared of V, and T of T squared is T cubed, and so on, forever. So if you understand this argument, then you obtain that T to the I plus, if T to the I of V, I plus 1 of V is T to the I of V, then T to the Jth iterate of T applied to V is T to the I of V for all J greater than or equal to I. That's the argument.
Professor, isn't it if T to the I plus 1 equals T to the I times T to the V?
Sorry, say that again, please.
That second to last line that you wrote, if T to the I plus 1 equals T to the I times TV, right? It's not T to the I times V, it's T to the I times TV, right?
No. So just look at this example. This is the case I equal 2. So T cubed of the applied to the vector space V is a subspace of T squared of V. So this is always true. But suppose, in fact, that T cubed of V is not only a subspace of T squared V, it's the whole thing. Suppose these are equal.
Oh.
All right. Then, if you take T to the fourth of V, that means apply T to T cubed of V. The T cubed of V is T squared of V. So this is T of T squared of V, which is T cubed of V.
So they all equal each other.
Which is T squared of V.
Yeah, I got it.
And you just bootstrap up one step at a time, and you see, and so So every power of T of V,
Is
2,
equivalent.
3, 4, 5, and so on forever, will just be T squared of V.
Thanks, Professor. I got it.
So this is in cryptography, in a chapter on digital signatures. Exercise 4.1. So Samantha is taking 2 primes, P equal 541 and Q equal 1223. And so these are her primes, and her public verification exponent E is 159853. So what is the public modulus that she gives to the world? It's the number n, which is the product of P and Q. So you have to multiply 541 times 1223, and you get 661,643. So this is the number that Samantha announces to the world. What is Samantha's private signing key? This will be a number D. And D has to have the property that D times E is congruent to 1 mod P minus 1 Q minus 1. So D must solve the congruence D times E. What is E? 159,853 times D, congruent to 1 modulo P minus 1 Q minus 1. What is P minus 1 Q minus 1? So you have to do the arithmetic. So if P is 541 and Q is 1223, then P minus 1 is 540, Q minus 1 is 1222, and when you multiply them together, you get 659,880. So you now have to solve the congruence. One 59853D congruent to 1 modulo 659,880. And I'm not going to do that because that takes 15 or 20 minutes of work. If you're doing it with a calculator, for example. And the way you can solve this congruence is you find, the greatest common divisor of these two numbers is 1. So you obtain that using the Euclidean algorithm, and then you work backwards and from the Euclidean algorithm find a solution for this congruence. So if Samantha is given the digital document D, which is 630579, and she wants to sign it so that people will know that in fact she has approved she has signed this document. Her signature S is going to be this number D raised to this number little d mod n. So this is a big calculation. I mean, it's a practical matter. You might want to do this on your laptop, so you can deal with not really big numbers, but bigger than you can do by hand or might want to do on a hand calculator. But that's how you solve this kind of problem.
Okay, thank you.
So this is cryptography. So this is on the RSA crypto system. And problem 3.9c. So,
Yes.
okay. So we're given a number n, which is a product of two primes, p and q, and the product is 109,404,161. And we don't know what p and q are, we just know what their product is. But we also know if you multiply p minus 1 and q minus 1 together, you get 10,938,612. And the problem is to find p and q, and they want us to use the method that is in remark 11. So remark 11 says what? Let's find remark 11. So the remark 11 says, if you take p minus 1 and q minus 1, and you multiply them out, you get pq minus p minus q plus 1. And pq is n. So this is n minus p plus q plus 1. So if we know n, and if we know p minus 1 and q minus 1, that will tell us what p plus q is. Because, let's see, let's just work out what is p plus q. So p plus q is equal to p minus 1, q minus 1. Sorry, p plus q is equal to n minus p minus 1, q minus 1 plus 1. Right? P plus q is n minus this plus 1. What is that equal to? N is 109,404,161. I subtract 109,380,000, sorry, 10 million. I just want to make sure I didn't write down these numbers wrong. Something doesn't look right. Problem 3-9. This is 109, 404, 161. This is 109, 380. That's what I thought. This is 612. So minus 109, 380, 612. If I subtract, what do I get? 11 take away 2 is 9. 5 take away 1 is 4. 11 take away 6 is 5. 3 take away 0 is 3. 2, 0. Let's see. Hope that's right. Let me just double check on my computer because I don't want to get the arithmetic wrong. If I can avoid it. 109, 404, 161 minus 109, 380, 612. That's 23549. And then I have to add 1. So this is equal to 23,550. So PQ is equal to this. P plus Q is equal to this. If I take the following polynomial, x squared minus nx plus, x squared minus p plus qx plus n. What is this? This is x squared minus p plus qx plus pq. This factors into x minus p, x minus q. So p and q are the roots of this polynomial. It's a quadratic polynomial. So I need to solve the quadratic equation x squared minus 25,550x plus 109, 404, 161 equals 0. So the worst thing, I mean, I can always just use the quadratic formula, or if you have a calculator that can solve a quadratic equation, or a computer that will solve a quadratic equation for you, 2550 times x plus 109, 404, 161 equals 0. Solve that for x. Let's see. Yeah. Let's see, something doesn't look right. Oh, this is a 3, not a 5. Always good to do my arithmetic correctly. This is 23550. And if you solve the quadratic equation, you get P is 6,367 and Q is 17,183. That's it. So if we knew the product of P and Q, and if we knew the product of P minus 1 and Q minus 1, then we can find P plus Q, and then we can write down this quadratic equation, and we solve it, and we find the primes P and Q. And you can check that if you multiply P times Q does equal N. Because you actually have to multiply these two numbers and see that this is what you get. So that's the solution.
Thank you.
So this is, again, cryptography. On chapter 3 on the RSA crypto system. And the problem is 3.1d to figure out what is x to the power 750, to solve the congruence, x to the 751st power is congruent to 677 mod 8023. So the first question we should ask is 8023 a prime number? And well, you can try and check it by hand. That would take a lot of work. But again, if you have a computer to use, even if you just took calculus at Lehman and learned Maple, turns out the answer is no. 8023 is not a prime number. And if you want to factor 8023, this turns out to be 1771 times 113. So what might be a way to try to solve this congruence? So there is a kind of a solution given in proposition 3.5. It says, I'm not going to write in the order in which it's written in the book, but let me write in the order which is useful to us. The congruence x to the e congruent to c modulo a product of two primes p and q. So this has the unique solution x congruent to c to the power d mod pq if e and p minus 1 q minus 1 are relatively prime, and de is the inverse of e modulo this, and de is congruent to 1 modulo p minus 1 q minus 1. So we know that our modulus 8023 is a product of two primes. So we can try to apply this proposition. So apply proposition 3.5 with P equal to 71, Q equal to 113, and E, my exponent, equal to 751. So the first question is, what is the GCD of E and P minus 1, Q minus 1? That's the greatest common divisor of 751 and the product of these two primes, 70 times 112. And you can calculate that out by the Euclidean algorithm if you like, but computers are certainly allowed. The greatest common divisor of 751 and 70 times 112 is 1. So if I can solve this congruence, DE congruent to 1 mod P minus 1 and Q minus 1, I can find the solution. So I want to solve the linear congruence. (751D) congruent to 1 modulo 70 times 112. 7,840. So if I can find a value of D that solves this congruence, then the solution, sorry, then the solution of my problem, which is x to the 751 congruent to 677 modulo 8,023, the solution will be x equals C (677) raised to the power D mod 8,023. So if I apply the Euclidean algorithm to these two numbers, I can find D, but that's just a calculation that would take 10 or 15 minutes or more right now. But I've reduced it to solving this linear congruence, and then you work your way backwards to solve the original problem. That's what has to be done. Okay, so we're back to linear algebra. Looking at linear transformations. And on page 238, number 20. So we have a linear transformation from 4-dimensional space to 3-dimensional space, given as follows. If you take the vector x1, x2, x3, x4 in R4, we're going to get a vector in R3, so there will be 3 coordinates. x1 plus x2, x3 plus x4, x1 plus x2, plus x3 plus x4. So this is a vector in R3. And what is the matrix with respect to the standard basis? So the standard basis in R4 is, I'll write it, say B sub 4. It has 4 vectors. E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0. E3 is 0, 0, 1, 0. and E4 is 0, 0, 0, 1. So that's the standard basis in R4. And in R3, let me call the vectors with the letters F. So F1 is 1, 0, 0. F2 is 0, 1, 0. And F3 is 0, 0, 1. So to calculate the matrix for T, we have to know how T acts on each of the basis vectors. So T of E1, which means T applied to the vector 1, 0, 0, 0, what is that? When x1 is 0 and every other coordinate is 0, we get 1, 0, 0. We get 1, 0, 1, which is 1, 0, 0 plus 0, 0, 1, which is F1 plus F3. That's T of E1. T of E2 is T of 0, 1, 0, 0. So when x2 is 1 and everything else is 0, I also get 1, 0, 1, which is F1 plus F3. T of E3 is T of 0, 0, 1, 0. So when x3 is 1 and everything else is 0, I get 0, 1, 1, which is 0, 1, 0 plus 0, 0, 1, which is F2 plus F3. And if I compute T of E4, which is T of 0, 0, 0, 1, when x4 is 1 and everything else is 0, this is again 0, 1, 1, which is F2 plus F3. So the basis, sorry, the matrix for T, it's going to be a 3 by 4 matrix. So T of E1, the coordinate vector for this is 1, 0, 1. T of E2, the coordinate vector with respect to the basis of F, is 1, 0, 1. T of E3, the coordinate vector is 0, 1, 1. And T of E4, the coordinate vector is 0, 1, 1. So this is the matrix for T with respect to these bases, the standard basis. Okay? Is there a question about any of that?
No, until now we are good. Thank you.
Okay, so that's the first part. And now I need to find the kernel and the image, the nullity and the rank. So the kernel of T, this is all vectors x1, x2, x3, x4, such that T of x1, x2, x3, x4 is the 0 vector. So this is the set of all vectors x1, x2, x3, x4. What is T of x1 and so forth? This is x1 plus x2, x3 plus x4, x1 plus x2, plus x3 plus x4. All the vectors such that this is 0, 0, 0. So this is all vectors x1, x2, x3, x4, where x1 plus x2 is 0, and x3 plus x4 is 0. And that automatically implies that x1 plus x2 plus x3 plus x4 is 0. So this is all vectors x1, x2, x3, x4, where this says x2 is minus x1 and x4 is minus x3. So this is all vectors x1, x2 is minus x1, x3, x4 is minus x3 for any values of x1 and x2. And I can write this as, I'll do it in several steps, x1 minus x1, 0, 0, plus 0, 0, x3 minus x3, all such vectors, which really means all scalar multiples of the vector 1 minus 1, 0, 0, and 0, 0, 1 minus 1. So this is the subspace of R4 spanned by these two vectors, 1 minus 1, 0, 0, and 0, 0, 1 minus 1. So the set of all linear combinations of these two vectors is the kernel, and these two vectors are independent. So what is called the nullity of T, which is the dimension of the kernel of T, is equal to 2. This is a two-dimensional subspace. It's a subspace spanned by two linearly independent vectors. So that's the kernel and the nullity. And then I need to try to calculate the image in the rank. So this is my, oops, where was it? This is my linear transformation. And what is the image of T? So this is all vectors, say y1, y2, y3 in R3, such that x1 plus x2 equals y1, x3 plus x4 equals y2, and x1 plus x2 plus x3 plus x4 equals y3. So it's all vectors where you can solve these equations. But another way of saying this is really all vectors y1, y2, y3, where y3 is y1 plus y2. Because if y3 is y1 plus y2, you can just let x2 equals 0, x1 equal y1, x4 equals 0, x3 equal y2, and so on. So this is the set of all vectors y1, y2, and y3 is y1 plus y2. And I can write this as a sum of two vectors. This is y1, 0, y1 plus 0, y2, y2. So this is all linear combinations of the vector 1, 0, 1 and 0, 1, 1. So the image of T is the subspace of R3 spanned by the vectors 1, 0, 1 and 0, 1, 1. And so the rank of T, which is by definition the dimension of the image of T, is 2. And we'll notice that the dimension of R4, which is 4, is 2 plus 2, is the dimension, is the nullity of T plus the rank of T. This is the big theorem about linear transformations, that if you have a linear transformation from one finite dimensional vector space to another, the dimension of the nullity plus the rank is the dimension of the domain of space. So this is linear algebra. Page 238. And which number?
23,
Number 23.
at least parts A and B.
So we have a linear transformation T from a vector space V to a vector space W. And R is the rank of T, which means the dimension of the image of T. So here's V, here's W. And sitting inside of W, we have the image of T, and this subspace has rank R. Okay. So the image of T is rank R. So let F1, F2 up to F sub R, these be vectors in W, which is a basis for the image of T. So what that means is, if each one of these vectors is in the image of T, there exists vectors x1, e1, e2 up to e sub r in V, such that T of EI is equal to Fi for all I going from 1 up to R. So a better picture might be, here's V, here's W, and F1, F2 down to F sub R. That's the basis for the image. And you have vectors E1, T of E1 is F1, T of E2 is F2, and so forth. T of ER is FR. So we want to prove that the set of vectors E1, E2 up to E sub n is linearly independent. So suppose we have scalars C1 up to C sub R, such that C1 E1 plus C2 E2 and so forth up to CR E sub R is 0. Let's say it's 0. The 0 vector is this linear combination. But T of 0, a linear operator, linear transformation always sends the 0 vector to the 0 vector. So 0 is T of 0. So that's T of C1 E1 up to C sub R E sub R. By linearity, because T is a linear transformation, this is C1 T of E1 and so forth up to CR T of E sub R. But each of these is the vectors F1 up to FR. This is C1 F1 and so forth up to CR F sub R. So I have a linear combination of the vectors F1 up to FR equal to 0. But these vectors are linearly independent. So these are linearly independent. So all of these coefficients, all of these scalars have to be 0, which means these coefficients, the same numbers. So the only linear combination of E1 to ER, which is 0, is the trivial linear combination with every coefficient 0. And that means the vectors E1 up to ER are linearly independent. Okay,
Yes, sounds good.
all right. Should I do part B?
If you have time, yes.
Yeah, of course. So again, I like pictures. I have T sends V to W. over here, I have the vectors f1 up to f sub r, which are a basis for the image of T. I have E1 up to E sub R back in V, where T of E1 equals F1 and so forth, down to T of ER equals F sub R. But I also have over here the kernel of T. That's everything which gets sent to the zero vector. So the kernel of T is the set of all V and V such that T of V is equal to 0 over in W. And this is a subspace. So it has a basis. So let's say the dimension of the kernel of T is K, and I let ER plus 1, ER plus 2, up to ER plus K be a basis for the kernel of T. And then I want to prove if I take these R vectors and then these K vectors, ER plus 1 up to ER plus K, I want to prove that the set of R plus K vectors is linearly independent. So suppose I can write the zero vector as C1, E1, and so forth, CR, ER, CR plus 1, ER plus 1, all the way up to CR plus K, ER plus K. So this is some big linear combination of these R plus K vectors. If I apply T to this, T of 0 is 0. So this is going to be C1 T of E1 up to CR T of ER, CR plus 1 T of ER plus 1 up to CR plus K T of E sub R plus K, because T is a linear transformation. But ER plus 1 up to ER plus K, they're in the kernel. So each of these vectors is 0. And again, the T of EIs are the Fs. This is C1 F1 up to C sub R F sub R. Because T of EI is T of E1 is F1 and so forth. And F1 up to FR are linearly independent. So C1 up to C sub R, those numbers are all 0. So if I go back to this linear combination, these numbers are all 0, and I get that 0 is CR plus 1, ER plus 1, up to CR plus K, ER plus K. But these K vectors form a basis for the kernel. So they're linearly independent. So all these coefficients have to be 0. So all R plus K coefficients are 0. So this set of vectors is linearly independent. So what I've constructed is very nice. I have, here's V, here's W, here's this linear transformation T. I have F1 to F sub R. That's the basis for the image. I have E1 up to E sub R. These vectors go respectively to these. And then I have the kernel, ER plus 1 up to ER plus K, and they all get sent to 0. And this set of vectors, E1 up to ER, ER plus 1 up to ER plus K, this is a linearly independent set. And I want to prove this is a basis for the whole vector space. So I know these vectors are linearly independent. What I must prove is that they generate the whole space. So suppose I take any vector in V. Then T of V is in W. But in fact, T of V is in the image of T, which is the subspace spanned by F1 up to F sub R. So T of V is some C1 F1 up to C sub R, F sub R. For some, for some scalars, F1 up to FR. Actually, I should write it like this. T of V is some linear combination of F1 up to F sub R. But F1 is T of E1. So this is some scalar, C1 T of E1, C2 T of E2, up to C sub K, C sub R, T of E sub R. Right? T of V is in the image of the linear transformation T. The image is spanned by the vectors F1 up to FR, and each of these F's is of the form T of E. If T is linear, so T of V is T of C1 E1 up to C sub R E sub R. So this vector equals this vector. So if you subtract equal things, you have to get the zero vector. But again, because of linearity, T of V minus T of this is T of V minus C1 E1 up to CR E sub R. So T of this vector is 0. So V minus this sum has to be in the kernel of T, which is generated by ER plus 1 up to ER plus K. So V minus this vector is a linear combination of these vectors. So you bring this to the other side of the equation, you get V as a linear combination of E1, ER up to ER plus K. That means the set of K plus 1 vectors spans the vector space. And that's what we had to prove. And it also proves that the dimension of the vector space is the dimension of the kernel plus the dimension of the image. That's the proof.
Sounds good. Thank you so much.
Okay, so I think that's it for right now. I'll be back this evening if there are more questions.